Hello students, welcome to my YouTube channel. This is the class 6 of lesson Magnetism and Matter. Hope all of you are understood the concepts which I have discussed in the previous classes. Now in the current session I will discuss about an important concept called as Curie's law and what do you mean by Curie's temperature, followed by I'll explain how the substances will exhibit diamagnetism, paramagnetism and ferromagnetism based on certain theories. Like those properties can be explained based on certain theories such as electron theory and domain theory. Those concepts I will discuss in the current session. Now let us get into the concept. The first thing I want to discuss is known as Curie's law. See, in the last session I discussed about diamagnets, paramagnets and ferromagnets. So paramagnets are those substances which are weakly attracted by external magnets. For example, given as aluminium, manganese are given, sodium is there, calcium is there. These are the substances belongs to paramagnets. In that, I have discussed about a concept called magnetic susceptibility. So symbol is given by Xi. I told what is magnetic susceptibility. This is a quantity, or you can say this is a thing which will represent acceptancy of a magnetic material or acceptancy of a material towards the magnetism. So higher is the magnetic susceptibility, higher is the acceptancy of magnetic field, less is the magnetic susceptibility, less is the acceptancy. And for diamagnets, you know this value is negative because they are repelled by the magnetic fields. Now, what Curie's law will deal with? The magnetic susceptibility of a paramagnets will depend upon temperature. Because at the beginning of the lesson I discussed, by increasing temperature or by disturbing the alignment or by dropping the magnets, you are able to decrease the magnetic property of a magnet. The same thing here, how temperature will affect the paramagnets, that will be described by Curie's law. Now what is the statement? The magnetic susceptibility of paramagnetic material is inversely proportional to the absolute temperature of the paramagnetic materials. This you can write this way also. Temperature is inversely proportional to Xi. Now, if T is taken as it is, if you remove the proportionality, you will get equal to followed by some constant. Constant is called as C. C stands for Curie's constant followed by Xi in the denominator. Now here, for understanding purpose, I will mention M, or you can write capital B also, which represents magnetic susceptibility. Now this is a mathematical form of Curie's law. So important for 1 mark. I repeat. Curie's law statement. The magnetic susceptibility of a paramagnetic materials is inversely proportional to the absolute temperature of the paramagnetic materials. In the sense, with increase in the temperature, the magnetic susceptibility of the paramagnetic materials decreases. So this is what Curie's law. Now, what is Curie temperature? See, both paramagnets as well as ferromagnets, magnetic susceptibility is inversely proportional to the temperature of the concerned materials such as paramagnet or maybe ferro. If you take the same rule in the case of ferromagnets, if you start increasing the temperature up to a certain extent, ferromagnets will not lose their property, means they will retain as ferromagnets only even if you are increasing the temperature. At a particular temperature, a ferromagnetic material will convert into para. In the sense, it will start decreasing, like losing its magnetic property. So, you know very well, ferromagnets are strongly attracted by magnetic fields and paramagnets are weakly attracted. Nothing but, if you increase the temperature, a ferromagnet which is able to strongly attracted by magnetic fields will convert into para. Nothing but, with increase in the temperature, its magnetic property is decreasing. Then, at what temperature a ferromagnetic material converts into paramagnetic material? Based on what? Magnetic property sample, not a total material will convert. Material will be as if, but its properties will shift from a ferromagnetic region to para. Then, the temperature at which a ferromagnetic material converts into paramagnetic material itself is known as Curie's temperature. For example, I have given certain temperatures as well as the materials list in the study material. Please go through it. See, in that cobalt, it's around 1394 degree Kelvin. At this temperature, cobalt, which is a ferromagnetic material, converts into para. Like I given for gadolinium, ferrous oxide, and you please try to get the values and corresponding materials. So hope you understood about the Curie's law and Curie's temperature. This for a we call Curie's law. The magnetic susceptibility of a paramagnetic material is inversely proportional to the absolute temperature of the paramagnetic material. With increase in the temperature, the magnetic susceptibility decreases, and after reducing the expression to the equal to, you will get a constant C, which is known as Curie's constant. And here Curie's temperature, which is a second definition. A Curie's temperature is a temperature at which a ferromagnetic material converts into paramagnetic material. So I have given an example here. The rest of the examples you can get through the material. Now let us get into the next concepts. So here the next concept is what? I will explain how diamagnetism, paramagnetism and ferromagnetism can be exhibited by the different substances. And what is the reason if you make a question mark? That question mark will give you answer as electron theory. In the sense, based on electron theory, I will explain now how diamagnetism will be exhibited and para, and based on a theory called domain theory, I will explain the ferromagnetic nature. So let us take an example of diamagnetic substance. Example, bismuth. So if you take a bismuth, you know every material is made up of atoms. Atoms consist of inside nucleus and around which electrons will be revolving. Now if you take a bismuth, the electrons will be in the paired state. If you take entire bismuth material, electrons will be in the paired state. See, every electron will have a different moments. For example, electron will revolve around the nucleus. Along with it will have a spin, past plus half or minus half. We might have got in chemistry also. Since the electrons which are available in bismuth are in paired state, then the net spin on the bismuth will become 0. In the sense, instead of considering as a spin 0, I will give an elaborate explanation. Assume this is first electron and this is second electron, and both are paired. Assume it has a plus half and this has minus half. It will have certain magnetic moment, it will have different magnetic moment. Magnetic moments are same, values are same, but the directions are opposite. Since they are in paired state, net magnetic moment becomes 0. Since the net magnetic moment of individual electrons is 0, then the total magnetic moment over the sample also becomes 0. That's the reason why bismuth exhibits diamagnetism. Now, hope you understood why bismuth is not able to attracted by the magnetic substances. Or you can say when magnet is placed near to the bismuth, instead of attracting, bismuth will get repelled, weakly repelled, since it does not have any magnetic field inside. Now what happens if you take such a diamagnetic material and when it is placed inside an external magnetic field? Assume if you are applying some external magnetic field on this. Now, in the presence of this external magnetic field, the velocity of this paired electrons will increases. So due to increase in the velocity, there is slight differentiation, since instead of like what I can say is pairing has happened, but there is slight distance will take place between these two electrons, because of which a small magnetic dipole moment will produce. But the dipole moment which is induced in these paired electrons will act opposite to the direction of the applied field. See, if any dipole moment produced in the electrons, if it is along the direction of applied field, it will get attracted. If it is against, it will get repelled. Then, I repeat once again, if you place any diamagnetic material in the presence of external magnetic field, because of this field strength, the velocity of the electrons increases, and due to which certain magnetic dipole moment will induce within the material, but the induced dipole moment will be in the opposite direction to the applied magnetic field. I repeat, the induced magnetic field in the sample, after applying the magnetic field, the direction will be opposite to the applied field. Since both applied field and induced field opposite, then in the presence of the external magnetic field, diamagnetic materials will get weakly repelled. hope you understood now why diamagnets will get repelled by the external when it is placed in the external magnetic field. So last conclusion is what? When any diamagnetic material is placed in an external magnetic field, there will be a small amount of induced magnetic moment develops, which is in opposite direction to that of the applied magnetic field. Since the induced magnetic field is opposite to the applied magnetic field, then the diamagnets will get repelled when it is placed in the presence of external magnetic field. So this is explanation of why diamagnets will have zero magnetic moment when there is no field, and why they will get a small magnetic moment when they are placed in the field, and why they will get repelled when they are placed in the presence of magnetic field. So this is in the case of diamagnets. So conclusion points is very easy. They have paired electrons. Net magnetic moment is zero. When they are placed in the presence of external magnetic field, a slight separation takes place. Velocity increases. Because of that only separation takes place. Magnetic moment will develop, and the developed magnetic moment, as if this is BH, stands for induced magnetic moment or magnetic field inside, that will act opposite to the applied. BA stands for applied, BI is induced. The directions being opposite, they will get repelled. So this is about diamagnets. Next, let us get into what? Para. So example, you can take it as manganese or sodium. Now in the case of para, what happens? If you compare with the diamagnets, I said in diamagnets the electrons are in paired state, but in para the electrons are in free state. So you make sure if these are the electrons, I mentioned the diagram clearly in the material. Electrons are not in paired state. Since they are not in paired state, spin cannot be cancelled each other. Since the spin cannot be cancelled, they have the magnetic moments. But the problem is what? Without any applied external magnetic field. For instance, this is the diagram you can imagine. Here this dot represents the electron and the direction represents magnetic moment of the each electron. Now, each that magnetic moment produced by the electron will act as a tiny magnets. Now the direction indicates, let's say this is from south to north. You can imagine this way because the direction of the magnetic moment is always from south to north pole. Here if you see the directions of these magnetic moments are in random, then the net magnetic moment over the sample becomes zero, since the magnetic moment of one electron will be cancelled by the magnetic moment of the another electron, since they are in random direction. See here and here, a lot of difference is there. Here they are paired. Since they are unable to get separate, the net magnetic moment is zero. Here the electrons are separate, they have magnetic moments, but the net magnetic moment is zero because the electrons have magnetic dipole moments in random directions, because each direction will get cancelled by the other one. Then how to get into a particular level, for instance to set it to a particular direction? So simply start applying magnetic field. So when you apply a magnetic field, external magnetic field on these paramagnetic materials, then automatically, see this way they will align. So you can find the difference in the diagram. Here the magnetic moments are aligned into a particular direction. Here also slight disturbance is there. That is because of due to thermal agitation. What is thermal agitation? Due to surrounding energy, thermal energy, the electrons will disturb. Even though they are placed in the presence of external magnetic field, the alignment will get disturbed due to thermal agitations and lattice vibrations and all. So because of this, the arrangement of the magnetic dipole moments of each electrons will be slightly aligned in the direction of the applied field. So here you cannot get exactly along the direction. Assume this line indicates the direction of applied field. In this direction, the dipole moments of the electrons will get aligned, but not perfectly. Why it's not perfect? Because the electrons will be under thermal agitation and vibration lattice. Due to these things, the electrons will get aligned approximately the direction of the applied magnetic field. When if this applied field is given, they compare to these two diagrams. Here the net magnetic moment is 0. Here the net magnetic moment is not equal to 0. Then automatically paramagnetic materials will get some magnetic field inside whose direction is along. See again here it's applied. Here it is induced. Since the direction is same, then paramagnets are slightly attracted, like I say, very feebly attracted by the magnetic fields which are placed externally. So this is how paramagnetic materials will behave when the field is absent and field is present. Now what is the conclusion points here? In paramagnets, electrons are in free state, they are not paired, they are in unpaired state. Each electron has its own magnetic dipole moment, but if we compare with the entire substance, the total magnetic dipole moment becomes 0 because electrons are set into different directions. In this sense, the dipole moments are set into different directions. So net magnetic dipole moment becomes 0. Then when an external magnetic field is applied, all the magnetic dipole moments will set into particular direction. That too in the direction of the applied field. But the setup is not so much perfect, all because these electrons will be under the disturbance of thermal agitation and vibrations due to the lattice. Then the net magnetic field induced inside will be in the direction of the applied field. Then automatically, since they are in the same direction, net magnetic moment, dipole moment is not equal to 0. Then paramagnetic materials are feebly attracted by the external magnetic fields. So this is in the case of dia as well as the para. Both are discussed based on what? Electron theory. Now when coming to the ferromagnetic materials, we are going to discuss based on domain theory. So let us discuss. So the points are mentioned in the material. Please watch the video carefully and read the points so that you can get clarity. So take a sample of ferromagnetic material. Example gadolinium, nickel, ferrous. Now if you observe this, here in ferromagnetic materials also, electrons are in unpaired state and they have their own magnetic dipole moments. But here the magnetic dipole moments will be in the case of groups. Means they will form into groups. Such groups are called domains. For example, in this region, the magnetic dipole moments will be in this direction. Now this one region is called domain. Now in this direction, here in this domain, the magnetic dipole moments are in this direction. Now here will be in this direction. It's not so particular, but just for approximation I am drawing here. So how many domains you can find here is 4 domains. That's the reason why theory is called domain theory. The reason here the dipole moments you can find in the form of bunches. But the bunches, if you take, all bunches are not in same direction. Again, the net magnetic moment here it is got 0. Dipole moment is 0 in the case of ferromagnets. Once if you apply some field, here the first case B is equal to 0. Once you apply field, based on the strength of the applied field, then there is a slight change takes place in the case of ferromagnets. What happened? All domains were set into the direction of the applied field. In the sense, along the direction of the applied field. Quickly. That's the reason why. Why quickly means here turning each magnetic moment is a bit difficult compared to turning the bunches. The process takes place very quickly here. That's the reason why ferromagnetic materials will be attracted very quickly when they are placed in the presence of external magnetic fields. Now, here if you compare, I have given 3 diagrams, slight changes and total changes happen in the case of magnetic dipole moments. So, this is the situation occurs when a ferromagnetic material placed in the external magnetic field. Now, if you check out the diagram, here induced dipole moment is 0. Here, induced magnetic dipole moment is not equal to 0 and it is along the direction of the applied field. So, A stands for applied, I stands for induced. Then, the direction is being same. Ferromagnetic materials are get attracted when they are placed in the presence of external magnetic field. Here, this conversion takes place very quickly. That's the reason why ferromagnetic materials will get attracted when they are placed in the external magnetic field in a quick instant. Whereas the direction of the orientation takes place a bit slowly and the direction will not be so much perfect in the case of para as they are slightly attracted or weakly attracted when they are placed in the presence of external magnetic field. Where in the case of dia, I said, the magnetic moment itself will be opposite to the direction of the applied magnetic field, hence they will get repelled. This is the reason why diamagnetism will exist, and paramagnetism will exist, and ferromagnetism. So today's concepts, just for a glance: Curie's law, where magnetic susceptibility of a paramagnetic materials is inversely proportional to the absolute temperature of the paramagnetic materials. Second, Curie's temperature, the temperature at which ferromagnetic material converts into para. I given one example and 3 more examples are mentioned in the material. Please go through it. Then I started explaining why diamagnetism and what happens when the diamagnet is placed in the presence of an external magnetic field. Same thing I have explained in the case of paramagnets as well as ferromagnets. So diamagnets and paramagnetism is based on the electron theory, and ferromagnetism is based on the domain theory. Hope you understood the concepts. Please watch the video carefully. If any doubts is there, please update me through WhatsApp and refer the study material. So when you are watching the video and parallel if you are referring, after watching the video if you refer immediately the study material, you will come to know what are the concepts. So thank you for the session. I'll catch you in the next session.